Okay, so welcome along. We're going to do Equilibria, Energetics and Elements from June 2010 today. So let's kick off. Some information here, give me some data to allow me to do this Born-Haber cycle. So I need to fill in the letters from this Born-Haber cycle, so let's see how we get on. First of all, D. This one here, formation of magnesium chloride is going to be this one. Magnesium solid going to magnesium gas is going to be the atomization of magnesium. This one is going to be the atomization of chlorine. This one is the first ionization energy of magnesium, so that's B. You can see it's going to Mg to Mg plus. And then this is going to be the second ionization energy of magnesium because it's going to Mg2 plus. The key thing that people leave out are the electrons here, so don't forget that. And then you've got your electrons going on to your chlorine to form the chloride ion. So that's the electron affinity of chlorine, which they've given me as being A. And then finally, the lattice enthalpy of magnesium chloride is going to be G. Right, they then want me to actually calculate the lattice enthalpy for this. So let's do that. So delta H lattice is going to be minus 642, which is this one here, D. Actually, what I'll do is I'll put the numbers on. Right, so what I've done is I've actually put the numbers on so that we can see quite clearly what's going on. Key thing to remember is you need to times this boy by 2, the atomization of chlorine, because I'm forming 2 chlorine atoms there. The other one you need to times by 2 is the electron affinity, first electron affinity of chlorine, because again you've got 2 chlorine atoms up there. So it is, to calculate that enthalpy, is this one here, the formation minus everything else, so minus 76 plus 2 times 150 plus 736 plus 1450 minus 2 times 349 for all of that. If you do the brackets, I'd recommend you do the brackets first. That comes to 1864, I believe, and that gives you the grand total of minus 2,506. Key mistake people make, they try and do it too quickly. I do your brackets first, and I would show your working, because you can get marks for the working, even if you stuff up your calculation at the end here. Okay, next thing is magnesium chloride has stronger ionic bonds than sodium chloride. Why? So you need to talk about the ions, always talk about the ions. So Mg2 plus has a higher charge than Na plus. Also, Mg2 plus is smaller than Na plus. So you've got a double whammy. Therefore, Mg2 plus has a higher charge density and stronger attractions, or stronger attraction to the Cl minus ion than Na plus. So you need your comparison there. Right, we're now going to move on to rates. So start off with to balance an ionic equation. So let's have a look at this. The oxidation state of bromine there is +5 and of bromide is -1, and it's 0 here. So hopefully you can recognise this is a disproportionation reaction. Right, we need to balance it though. So -1 to 0 is a change of +1, and +5 to 0 is a change of -5. So I need 5 of those ones to balance out which to balance out my bromides mean I need 3 of those to get it to work out. Once I've done that, to balance out my oxygens there, I need 3 waters there, which means I need 6 H pluses there. Right, okay, so I've now got some rate data, and what they're going to ask me to do is they want me to use these results to work out my rate equation and then calculate the rate constant. So let's do that. First of all, I'm going to calculate BRO3 minus, look at the rate for that. Hopefully the key thing that you can see is from the graph, so from the graph, rate versus concentration, you have a straight line through 0, 0. Key thing, do put through 0, 0 through the origin, and therefore it is first order with respect to BrO3 minus. So we've sorted out this boy here. Let's look at Br minus now. If we just compare these ones, that stayed the same, that stayed the same, that's nice and easy. Hopefully you can see that's times by 2 and that's times by 2, and therefore we can also say is going to be first order with respect to the bromide ion. So when you explain it, you say, as I double the concentration of Br minus, I double the rate, and therefore it is first order with respect to Br minus. H plus, I would probably, if you see that stayed the same, that stayed the same. From going to there, I doubled it, and going from there, I've actually times the rate by 4. So again, you would say, as you double the concentration of H plus, you quadruple the rate, and therefore it is second order with respect to H plus. Okay, so that then gives me this rate equation here. Rate constant, first order, second order. I need to find the rate constant K, so I can rearrange that to give me is equal to rate divided by Br minus BrO3 minus H plus squared. Then you pop in the results, maybe from the first experiment, doesn't matter. So I'm going to use the first one. So the rate was 1.19 times 10 to the minus 5, and that was over 5 times 10 to the minus 2, 1.5 times 10 to the minus 1, and 3.1 times 10 to the minus 1 squared. I would work this out first, just to show the examiner you know what you're doing and they can follow you. It is really annoying when you're marking papers and you're trying to follow a calculation which they've stuffed up, and you want to award marks but you can't. So you've got that, that works out to be that. So that equals 0.0165 as your numerical value. You now need to work out units. Rate is in moles per decimeter cubed per second. Your concentration is going to be in moles per decimeter cubed to the power of 4. That's going to cancel with that to give you 3. So it's going to be moles to the minus 3, decimeters to the 9, seconds to the minus 1 for your units. Right, this is a slightly odd one. Explain how the student could prove that propionate acid was weak by taking a single measurement, and then how can I calculate Ka for propionate acid? So the first thing you would say is, obviously if you use a pH meter, the pH should be greater than 1 for it to be a weak acid. So 1 bar, pH should be greater than 1. Then, how do you work out Ka? Well, you know the concentration of H plus is 10 to the minus of your pH value that you would have measured. Ka then is H plus squared over your concentration of HA, which is H plus squared in this example over the concentration of propanoic acid, like so, or H plus squared over, because they've given it to me, 0.011, and then that would give you Ka. So the student measures the pH of some sodium hydroxide, calculate the concentration of that. There's various methods to do this. This is my way that I do it. I would work out your P, you know that POH is 40 minus your pH, which is 13.46. That comes to 0.54, and then your concentration of OH minus is going to be 10 to the minus 0.54, which gives you 0.29 moles per decimeter cubed. Okay, it's buffer time. So, propanoic acid, excess propanoic acid was mixed with sodium hydroxide, form a buffer Y. Okay, so first of all, where you can, stick in an equation. Propanoic acid, remember you've got it in excess, is going to react with sodium hydroxide to form sodium propanoate, which is your salt of your weak acid. But because propanoic acid is in excess, you've still got some of that remaining, so some still remains. Therefore, you've got yourself a buffer. Right, once you've got that, you can then do your buffer equation. So propanoic acid is in equilibrium with propanoate plus H plus. And then you can say if you add OH minus, that's going to react with the H plus to give you water, and the equilibrium will shift to the right hand side to replace the H plus. If you add H plus will react with this boy to give you propanoic acid, and equilibrium will shift to the left hand side. Right, okay, time to look at a couple of acids now. I've got nitric acid and propanoic acid. Nitric acid is going to be the strong acid here. It's going to be stronger than propanoic acid. So, he is going to be acid 1, which means he's base 2. That is going to lose a hydrogen to form the nitrate ion, which is going to be base 1. This guy is going to accept a proton, like so, and therefore he is acid 2. Remember, your conjugate pairs must differ by H plus. So always make sure they differ by H plus. The key thing to spot here is he was a strong acid. Right, okay, now we're going to react propanoic acid with reactive metal. So first of all, propanoic acid with magnesium. The difficult thing here, I suppose, is working out your formulae. Remembering that magnesium, of course, in group 2 has a charge of +2. Remember, it's amazing what you forget from AS chemistry. And that's also going to give you hydrogen gas like so. And then you also got the ionic equation. This one you can just learn is H plus CO3 2 minus, and you need 2 of those to give you CO2 plus H2O. Really, that's one it's worth learning so that you can bang that one out in the exam nice and easy.